Chapter 1, Introduction. In today's world, data is everywhere. This guide is for the people who have to make sense of it all. It gives you a set of core principles and points out common traps to avoid. While the guide provides rules, the best data analysts know when to break them. But for most of us, most of the time, following these guidelines will lead to clearer, more reliable results. Chapter 2. It all starts with a good question. Before you dive into a pile of data, you have to know what you're looking for. Your data can't answer every question, so it's vital to ask the right kind of question. Here are the main types. Descriptive. This is like taking a snapshot. You're simply summarizing what you see in the data. Think of the U.S. Census. It tells you how many people live where, but it doesn't explain why. Exploratory. This is about discovery. You're sifting through the data to find interesting patterns or trends that might lead to a new idea or hypothesis. It's like being a detective looking for initial clues. Inferential. This asks, does the pattern I see in my small group also apply to a much larger group? This helps you figure out if a finding is a fluke or a real phenomenon. Predictive. This is about forecasting. You use the data you have to make an educated guess about the future. A classic example is using polling data to predict who will win an election. Causal. This is the toughest question to answer. It asks, if I change one thing, what will happen to another? To answer this, you usually need a carefully controlled experiment, because just because two things happen at the same time doesn't mean one caused the other. Mechanistic. This is the super specific version of a causal question. It tries to figure out exactly how changing one thing will always and only change another. This is more common in fields like engineering. Watch out for these common slip-ups. Confusing correlation with causation, building a predictive model and testing it on the same data, a big no-no called overfitting, or finding a significant result just by trying hundreds of different models until one sticks. That's called data dredging. Chapter 3. Tidying up your data. Imagine trying to cook in a messy kitchen. It's frustrating and inefficient. The same goes for data. Tidy data is a way of organizing your information so it's easy to work with. A complete tidy data package includes 4 things. 1. The original, raw data. 2. The clean, tidy version of that data. 3. A code book that explains what each variable means. 4. The exact steps or recipe you used to clean the raw data. The golden rules for tidy data are simple. Every variable gets its own column. Every observation, like a single person in a study, gets its own row. Different kinds of information should be in separate tables, linked by a common ID. Chapter 4. Giving your data a quick health check. Before you start your analysis, you need to get to know your data. Think of this as a quick checkup to spot any issues. You'll want to understand the different types of variables you have, like continuous numbers, ordered categories, like small, medium, large, or unordered categories, like red, green, blue. Most importantly, look for problems. Are there obvious typos, outliers that seem way off, missing values? Understanding these quirks from the start will save you a world of trouble later. Chapter 5. Exploring your data. This is the fun part. Exploratory analysis is about making plots, creating summary tables, and just playing with your data to see what you can find. The goal here isn't to create a beautiful, polished report, but to have a conversation with your data. Some tips for good exploration. Be quick and messy. Don't spend hours making one perfect graph. Make dozens of quick ones to get different views. Plot the actual data points, not just summaries like averages. This helps you see the full picture, including outliers. For huge datasets, it's okay to work with a smaller sample to speed things up. If your data spans huge ranges, from 10 to 10,000 for example, try plotting it on a log scale. It often makes patterns much clearer. Chapter 6. Making sense of it all with models. Statistical modeling is how we use a small sample to make an educated guess about a whole population. Inference is how we talk about how certain we are about that guess. Key ideas to keep in mind. Be honest with your data. If you can, use one part of your data to explore and a separate part to confirm your findings. This prevents you from fooling yourself. Know your biases. Think about how your sample might be different from the larger population you care about. Don't ignore outliers or missing data. They can have a huge impact on your model. If you're testing many things at once, you have to be stricter about what you call a discovery. Otherwise, you're bound to find false positives just by chance. Don't just trust a p-value. Always look at the confidence interval, which gives you a range of plausible values and a better sense of the real-world meaning of your result. Chapter 7. Predicting the Future with Machine Learning. Prediction is all about building a system that can make forecasts for new situations. Think of a spam filter or a movie recommendation engine. The process usually looks like this. 1. Split your data first. Before you do anything else, set aside a test set that you don't touch. You'll use this at the very end to get an honest measure of how well your model works. 2. Focus on features. Getting the right data and preparing it well is often more important than having the fanciest algorithm. 3. Use cross-validation. This is a clever way to use your remaining training data to build and test your models without peeking at your final test set. 4. Consider blending models. Often, averaging the predictions from several different models gives you a more accurate and stable result than relying on just one. Remember, prediction is full of trade-offs. Sometimes you have to choose between a simple, easy-to-understand model and a complex one that's slightly more accurate. Chapter 8. The Quest for Causality. This is the holy grail of data analysis, figuring out if one thing truly causes another. The most important takeaway is this: correlation is not causation. Just because ice cream sales go up when shark attacks increase doesn't mean ice cream causes shark attacks. The real cause is summer weather, which leads to more swimming and more ice cream eating. The best way to find a cause and effect relationship is with a randomized controlled trial. Without one, claiming causality is extremely difficult and requires a lot of careful assumptions. Be very cautious with causal language like impacts or leads to, unless you have the evidence to back it up. Chapter 9. Writing up your analysis. Your analysis isn't done until you've communicated it. A good written report tells a clear, compelling story about your data. Structure it like this. Start with the question you're answering. Describe your data and your methods. Present your results, making sure to include your measures of uncertainty, like confidence intervals. End with your conclusions and be honest about any potential limitations or problems. Chapter 10. Creating Great Figures. A good graph can be worth 1,000 words. The key is to make your figures clear, honest, and easy to understand at a glance. Some pro tips. Let position do the talking. Our eyes are great at comparing lengths and positions on a single scale, which is why bar charts are often better than pie charts. Don't be afraid of color and size to add extra layers of information. Use clear, plain language labels. Your axes and title should make sense to a non-expert. Write a self-contained caption. Someone should be able to understand the main point of your figure just by reading the caption. Avoid dynamite plots, bar charts with a single arrow bar on top. They hide the underlying data and can be misleading. Chapter 11: Presenting your data. Giving a talk is about connecting with people and getting them excited about your work. It's more of a performance than a lecture. The secrets to a good presentation. Tell a story. Start with the problem, walk through your process, and reveal your findings. Use huge fonts and minimal text. People should be listening to you, not reading your slides. Walk the audience through every figure. Explain the axes, point out the key trends, and tell them what to look for. Finish on time. It's the most respectful thing you can do for your audience. Chapter 12: Making your work reproducible. Reproducibility means that someone else can take your data and your code and get the exact same results you did. It's a cornerstone of scientific trust. How to do it? Use a script, like an R Markdown or Jupyter Notebook, that contains all your code, from data cleaning to figure generation. Keep things organized in separate folders for data, code, and figures. Use version control, like Git, to track your changes. If you use random numbers, set a seed. This ensures the randomness is the same every time the script is run. The ultimate test: have someone else try to run your analysis from scratch. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.